so just quick review from yesterday. Okay, there's two types of interference. Constructive interference, in which the waves are in phase and the amplitude increases. And there is destructive interference when the waves are out of phase and they cancel each other out and the amplitude decreases. Now, they don't always obviously completely cancel one another out, but they make the amplitude smaller. And we looked at that at the end of the day when I showed you, here's exactly what I'm going to ask on the unit exam. Here's two waves occupying the same space. Draw what it would look like now. Okay, so that's what you're going to get in terms of one-dimensional waves and interference. The next thing we have to look at is two-dimensional waves and interference. Okay, so this is more about like sound waves and even light waves, where do they interfere and what does that look like, sound like, etc. Okay, so if I have this situation here, okay, where I've got an amplifier and it's producing just a tone. Okay, we're not saying like it's playing music or you're watching a movie or something like that where the sound is constantly changing. Okay, it's playing just a constant tone. Okay, so what's happening then is if I'm exactly the same distance away from both speakers, there's the same number of wavelengths traveling to me from the speakers, from each one. Okay, so they're going to arrive in phase, and I'm going to hear a sound that is actually louder than what is being produced. Okay, so let's say that the sound being produced is like 50 decibels. Okay, that's about normal conversation level. Okay, when I'm standing here, I'm going to hear a sound that's louder than that because these two waves are meeting together and interfering constructively, making the amplitude double. Right? And so as a result, standing in that position, I would hear a louder sound than the speakers are actually making. Right? Which means I'm getting free amplification at that location. Okay, everyone okay with that idea? All right, so that happens as long as the waves arrive in phase. The only way they arrive in phase is if they are coming from these speakers and arriving at the same point in the wave. So if I move from this position so that I'm farther from one speaker than the other, would I get that situation again? The answer is yes and no. It depends where I stand. What determines whether I hear a loud sound due to constructive interference or a quiet sound or no sound at all due to destructive interference is the number of wavelengths that travel from each speaker. Right now, there's one wavelength, two wavelengths, three wavelengths from that speaker. And there's 1, 2, 3 wavelengths from that speaker. So they arrive at the same point in the wave, and I get constructive interference. If I back up and I'm over here instead, so I'm at a point where there's 3 wavelengths from this speaker and 4 wavelengths from this speaker, do I still have a constructive interference situation? I do. Because it's a full wavelength. They're still arriving at the same point in the wave, and they're still going to interfere constructively, even though they've had to go 4 wavelengths from this one and 3 from this one. Now, what if instead I stand here, where it's 3.5 wavelengths from one speaker and 3 from the other? Then what do I do? So now I've got waves coming from one speaker that are coming in as a crest, but the other waves are half a wavelength further. So they're not coming in as a crest, they're coming in as a trough, right? A crest and a trough. So if I've got a wave, okay, and it looks like this, okay, this is the crest, this is the trough, this is one full wavelength. A crest and a trough are half a wavelength apart. So if one set of waves has to travel a half a wavelength different from the other, they're going to arrive out of phase. One is a trough, one is a crest, and they're going to cancel. Okay, you want to follow me there? Okay, so what you want to do if you're setting up like, a home theater system or even like a big theater, okay, concert hall or something like that, is you want to arrange and build the walls and sources of sound so that the places that people normally sit are going to be areas where waves are going to generally interfere constructively and improve the quality of the sound that they observe. Okay? If I have too many dead spots, Okay? People aren't going to like that. Okay? If I go to a concert and I pay good money for the tickets, I don't want to sit behind the pole, okay, and be in a spot where the sound is interfering destructively and I don't hear good quality sound and I can't see the stage. Okay? I'll be upset with my purchase. Everyone kind of follow there? All right, so let's say that I've got these two speakers, like we see in the diagram here on the right. Okay, so all the stuff coming out of speaker A is the light blue lines, and everything coming out of speaker B is the dark blue lines. If I am standing right here, will I hear a loud sound or a quiet sound? Loud. Okay, because I'm standing where two lines overlap. That's two crests. Every line represents a crest. Okay, so there I would hear constructive interference because I'm two wavelengths from speaker B and I'm 1, 2, 3 wavelengths from speaker A. The difference in travel is a full wavelength, so they're one full cycle different and they still arrive in phase. Everyone okay with that? All right. What if I stand instead right here? Now what do I get? Yeah, quiet sound, or if this is like a perfectly anechoic chamber where there's no stuff that can bounce off the walls, I'll hear absolutely nothing standing at that point because I will have total destructive interference. I'm standing at a spot where I'm on a crest from speaker B. I'm exactly 3 wavelengths from speaker B, but I'm 1, 2.5 wavelengths from speaker A. So I'm sitting in a crest from speaker A and a trough from speaker B, sorry, the other way around, okay, and I'm going to have complete destructive interference. Okay? If you could actually set this up in a perfectly anechoic chamber, you would actually be able to walk around the room and hear the sound go up and down, just based on where you were in the room. You'd be able to stand in a spot where even though the speakers are playing a sound, you hear nothing. Take a step to the right, and you're going to be covering your ears. Okay? Because it's going to be so loud, right? Just based on where does the interference happen. Okay? That doesn't happen in normal situations because walls echo. Okay? And every sound that's made in this room is going to bounce off the walls a little bit, and you're never going to get those spots that are totally dead. Okay? If I put two identical tuning forks up here and just struck them both, you would be able to walk around the room and kind of detect changes in the volume, but you'd never be able to find a place that was totally dead. Okay? Does that sort of make sense? Okay. So, if they're in phase, then we're going to get constructive interference. We're going to hear a loud sound. Okay? If they're out of phase, like we were saying, if I'm 3.5 meters from this one, that's 3.5 wavelengths in this case, and 3 wavelengths from this one, then I'm arriving out of phase and I hear destructive interference, quiet or no sound at all. All right? So the thing that determines that is the wavelength of the waves and the distance they have to travel. Okay? Those two things determine whether they arrive in phase or out of phase. All right with that idea? So, if I had these two speakers here, okay, and I was setting up somebody's like home theater system or something like that, okay, here, here, and here would be good or bad to put seating. Good. Okay? These are areas of constructive interference, at least for that tone. Okay, for that particular frequency. It wouldn't be true for every frequency. Okay? Whereas here and here, okay, I'd hear basically nothing because those are 2 points of destructive interference. Right? And actually, if you get your home theater system professionally installed where you really know what you're doing, okay, you can actually set up a home theater amplifier so that it delays certain frequencies from opposite speakers in order to create areas of constructive interference where you are seated, no matter what the frequency of the sound is. Okay? You can adapt it to do that. Right. You have to really know what you're doing in order to make that work, but it is an adjustment that you can make. Yeah, really, really want it badly though. Okay. The easier solution is just get bigger, louder speakers. I like that. Okay. So, here's how this would work. This is exactly what I'm going to ask you on Tuesday on your unit exam. So write this question down. Okay? I'm going to ask a question just like this. It's about interference, but it makes us use interference principles, universal wave equation, and Pythagorean theorem. Okay? A couple of things. All right, so I'll give you a couple minutes there to get that written down, and then we'll walk through it. Okay, so let's have a look at how this one works. So we just said a few minutes ago that what determines whether you hear a loud sound or a quiet sound is the number of wavelengths that travel from each source, okay, to the observer. Right? If it's a whole number of wavelengths, so 4 from one and 2 from the other, or 3 from one and 3 from the other, or 20 from one and 205 from the other, as long as it's a whole number of wavelengths difference, okay, you'll hear a loud sound. If there's a half a wavelength difference, then I'm going to hear nothing. So if I have 2.5 from one and 3 from the other, I get destructive interference because one's arriving as a crest, the other's arriving as a trough, and they cancel each other out. Okay? If one comes in at 9.5 and the other comes in at 20, it's still a half wavelength out of phase, and that means that they're going to interfere destructively. Okay? Everybody with me there? All right. So if I'm going to determine whether this person here hears a loud sound or a quiet sound, I need to know how many wavelengths are going to be between this speaker, okay, we'll say this is speaker A and the observer, and how many wavelengths are there from speaker B to the observer. So what are some pieces of information I'm probably going to need? No. Yes, I'll definitely need the 2.4 meters. What else will I need?
Frequency.
Okay, I'll need the frequency. I actually don't need it to do what I'm going to need it because I have to use it to get what I want. What's the other thing that I want?
The hypotenuse.
Okay, I'm going to need to know the hypotenuse of this triangle. That's for sure. Okay, so why don't we calculate that first? So we're going to do square root of 3.2 squared plus 2.4 squared. It's exactly 4 meters. Okay, still one other thing. I need to know how many wavelengths there are from each speaker to the observer. What do I not have that I need? Wavelength. Okay, if I'm going to determine the number of wavelengths from one speaker to the observer, I need to know the wavelength of the waves. Okay? It's great that I know how far it is from one speaker to the observer and the other speaker to the observer, but I need to know how many wavelengths are there here. In order to do that, I need to know what the wavelength is. Okay? Everybody follow me there? So this is where the universal wave equation comes in. Okay? The information I have is that the frequency is 214 hertz. Okay? The speed of sound is 343 meters per second. That means I can calculate wavelength using the universal wave equation. Okay? So V equals F times lambda, so lambda will equal V divided by F. 343 divided by 214 is 1.6 meters. Pretty sure. Not times, divided. Okay, 1.6. All right, so now I know the wavelength is 1.60 whatever meters, and I would keep all those decimals in my calculator. All right, so each wave is 1.6 meters. Now I need to know how many wavelengths are there from speaker A to the observer and speaker B to the observer. How do I find that?
You divide the length of each speaker by the wavelength.
Exactly. I divide the length of the distance between the speaker and the observer by the wavelength, and that'll tell me the number of wavelengths. Okay, so 2.4 divided by 1.6 should be 1.5 wavelengths, yes? Okay, so there's one wave and a half a wave. Okay, 1.5 wavelengths. Now I need to do the same thing here. Okay, I've got to figure out how many waves are there here. So I'm going to go 4 divided by 1.6. That's going to be 2.5, right? Yeah. All right, so from this speaker, there's 1, 2 and a half. Okay. Am I going to hear a loud sound or a quiet sound? Okay, as long as they arrive at the same point in the wave, I'm going to hear constructive interference. Is there a difference of a half a wavelength here, or is there a difference of a whole wavelength here? A whole wavelength. That's why I drew it on. Okay, this is 1.5. It's arriving as a crest. This is 2.5. It's arriving as a crest. Okay, the difference is 2.5 minus 1.5. 1 full wavelength difference. Okay, that's what determines whether you're loud or quiet. If the difference is a whole wavelength, okay, or 2 whole wavelengths, or 500 full wavelengths, as long as it's a whole number, it's constructive. Okay, if I get 2.5 or 3.5 difference, okay, so then I would have destructive interference. Does everyone follow me there? And so it's the difference in travel, difference in the number of wavelengths. 2.5 minus 1.5 is a whole number of 1. Okay, so that's constructive interference. That is exactly what I will ask on Tuesday, on your unit exam, okay, for interference.
Will the right side triangle be set up already so we know which is the hypotenuse?
You might have to calculate one of the sides, but I'll give you enough information to do it.
Yeah, if you know what I mean, so you don't like subtract them when you do the Pythagorean theorem, or add, so you know what you're going to do.
Yeah, like I'm not kidding you when I say it's going to be exactly like this one. All I'm going to do is like change the frequency. Yeah. So it's really, really like this one. Yeah. All right, so that's all we got for interference. So now we're done interference. We're going to move on to wave behavior. Okay, so that's the next thing here. Okay, so interference leads to what do waves do when they're traveling? Okay, how do waves behave? Okay, what do waves do when they move from one medium to another? Right. Now, we've already kind of talked about that a little bit. We know that when a wave goes from one medium to another, 2 of its properties will change. What are they? One of it is speed, and the other is? Okay, height might change. That wasn't what I was thinking of, but it's true. Okay, and one other one. Wavelength. What can't change? Frequency, right. Okay, so learn what happens when a wave encounters a boundary. Well, when a wave goes from one medium to another, some of it will be reflected, some of it will be transmitted, some of it will go through, some of it will bounce off the boundary. Okay, but its wavelength and its speed will change.
Just to be like it relates, but it's a little random. Unlike airplanes, when they ask you not to use technologies, because like there's a chance it interferes on that frequency, if like it's similar.
There's a chance it could interfere with some of the instrumentation on the aircraft. I don't know what instrumentation, okay, but I'm also not going to do something that's going to screw up a plane I'm on. Yeah, okay. I don't know if that's like a real thing or not, but I'm going to trust that I don't want the plane to crash. Unlike dude who's on his phone when they say not to be. It makes me want to like crush the phone and be like, I want to die. I'm sure there's something that it can interfere with, or they wouldn't ask you not to be on it, right? It's not a matter of, well, it'd just be safer if you were paying attention than we crash. I don't think it's that. Okay, learn what happens. So we talked about that. Understand that while many characteristics of a wave change upon entering a new medium, frequency never changes. I think we've only said that about 50 times. But it's important because, hey, frequency never changes. So, okay, and learn what happens when the properties of a wave change. Okay, so we're going to be kind of looking at that stuff here today. Okay, so obviously waves can go through lots of materials. Okay, some waves travel through some materials very easily. Some waves travel through the same material not at all. Okay, so for example, sound travels through the door just fine. Light does not. Okay, and that's okay. They're different kinds of waves. Okay? Longitudinal waves work differently than transverse waves. Light is a transverse wave. Okay? So something that's opaque to a transverse wave might be transmissible for a longitudinal wave. All right, but when they do go through these different materials, their speed is different, okay? Because we know the medium controls the speed of the wave, okay? So the speed of the wave is determined by the medium itself or the properties of that medium. And we were saying the other day, cold air, speed of sound is slower in cold air than it is in hot air. Okay? It's the properties of the medium that control the speed of the waves. Okay? Now you can see this with light quite easily because light refracts. Well, all waves refract. They bend. Okay? But you can see it with light. When light enters a new medium, its direction changes. Okay? I'll show you this in just a minute. Okay? You got to trust me. It does. Okay? When you go into a new medium, the direction of the light changes. And the reason for that is that its wavelength and its speed are changing. But it stays the same color because its frequency, nothing changes. Okay. All right, so I'm just going to grab a couple of things out of the back room here, guys, and I'll show you kind of what I'm talking about. Okay, so is everybody all right with that idea that waves travel different speeds? We can clearly see that in real life. Okay. Okay, so when wave energy is hitting a boundary between two medium, some of it is going to be transmitted, and we saw it. Some of the wave gets through. Some of it gets reflected. That is always the case. Okay? At any boundary, some wave energy will get through, and some will not. Okay? The only time you wouldn't have that is if the boundary was actually between two identical media. So if I put two identical slinkies together, it's not really a boundary. Right? The medium is the same. I've just attached two things that are identical, so I'm not going to see any difference. Okay? But if there's any difference between the two media, some of the wave energy is going to get reflected off of that boundary. Okay? If the boundary is not so much a boundary as it is a fixed end, so the medium is actually attached to something that can't move, okay, then none of the wave energy really gets through it. It all bounces off. Okay? It comes back. All right. So this is rare. This is never like an all or none kind of phenomena. Okay, if I make this pulse here in the more dense medium and it goes into the less dense medium, okay, then I get a pulse that is going to travel faster. Okay, and as a result, the pulse will also be longer or shorter? Longer. Okay, so this pulse gets longer, and my reflected pulse is upright. So if I go from slow to fast, I get an upright reflected wave. You have to memorize that. Okay? You'll have to memorize that. If I go from a slow medium to a fast medium, the reflection off the boundary is upright. Okay? That is, it's the same as the incoming wave. If we go the other way, okay, like you saw when I was making the waves that were going towards Noah, okay, I'm going from the fast medium to the slow medium. And when that happens, the wave travels slower, is shorter, and my reflected wave is inverted, okay, or upside down. Okay? And those are the words that you'll get, upright and inverted. Sometimes a textbook will also use, instead of upright, it'll use erect. But everyone laughs when I say that, so I don't say it. Okay? All right, everybody good with that? So that thing you just have to remember, because here's how I'm going to ask this on your test. I'm going to show you a before, a during, and an after diagram. Okay? One's going to show some pulses, okay? And then it's going to show it a little while later. But now there's going to be some different pulses. Some are going to be traveling backwards. And you're going to have to tell me, was this medium more dense or less dense or faster or slower than the first one, based on what do you notice about the pulse and what do you notice about the reflected pulse? Okay? If you're looking at a diagram where you've suddenly got this pulse that's way longer in the second medium, okay, and this tiny little pulse coming back that's upright, then you would say, oh, I'm traveling faster in the next medium. Whereas if I have this really tiny short pulse okay, in the second medium, and I've got this big inverted pulse coming back in the first medium, then it would say that was a slower medium that it was going into. Okay, so that's how that's going to be tested, okay, on Tuesday. Okay, so if wave energy reflects from a more dense medium, okay, the reflected wave will be inverted. That's what we just talked about. If it reflects off a less dense medium, then it results in an upright wave coming back. Okay. Yes. Okay, and this is what would happen, guys, if I had that slinky and it was just lying on the floor and I just made a wave in it, okay, the wave would travel through the slinky and then it would go from the slinky into the air, which is way less dense. So I would get a really, really small upright wave coming back to me. Okay, after I do that. Whereas if I had the slinky attached to the wall, when I made that wave, the wave would hit the wall and bounce back, but it would be upside down, right? It would be inverted, okay? Because the wall is way more dense than the slinky. All right. Okay, now how many people have played pool before? Okay. How many of you can consistently hit a bank shot? Okay. And not everyone's quite as confident on that, right? Okay. There is a trick to this. To hitting a bank shot consistently every time, there's just a small trick. Now, again, your cue ball can't be spinning at all, okay, when you do this. It has to be just rolling. Okay? But you can sight this out and hit a bank shot every single time if you use what we call the law of reflection. Okay? The law of reflection says this. Whatever the angle the wave comes in at, that's the angle it'll come off at. The angle of incidence equals the angle of reflection. That is the law of reflection, and it is always true. If you've ever tried to shine, reflect the sun into somebody's eyes off the face of your phone, okay, you're using the law of reflection, right? You have to get the angle right. You got to catch the sun and go get it over that way, okay, and get it in their eye. Okay, well, that's using the law of reflection. It's the same thing to make a pool shot or a bank shot in pool. So, what I have to do in order to make this work is I have to imagine that the bumper, which is my reflective surface, is like a mirror. Because it is. It's a reflective surface. Okay? Not for light, but for balls. Now, if I stand in front of a mirror, how far behind the mirror is my reflection? Okay, if I'm 1 meter in front of a mirror, how far behind the mirror is my reflection? 1 meter. Okay, that's the key part of this. Okay, anytime you have a plane reflective surface or a flat reflective surface, your reflection is the same distance behind the surface as you are in front of it. So, what I have to do is know how far this ball that I want to hit is from the reflective surface. Then I have my friend stand that far behind the reflective surface with his pool cue right in front of him. Okay? Now, all I have to do is look from where I'm at I drew that crooked. And sight for his pool cue, and I will make that bank shot every single time. Okay? This is how you hustle pool. Okay? My friend and I in university, this is how we would hustle pool. Okay? Because you could hit, we were both in physics, so we knew this. Right? We could get tricky shots, whatever, like, well, we can hit a bank shot whenever we want. Okay? One of us would just stand, and nobody really notices that you're doing it. You're just kind of standing there, leaning on the pool cue, looking like you're totally innocent. But you're sighting, your friend is using it as a sighter to hit the bank shot properly. It's kind of cheating, but only if you get caught. Okay? So that's what we would do. Okay? We only had one person who actually figured out what we were doing. He got really mad. He was really drunk. But yeah, he got really mad. Like, you're cheating. We're like, no, we're using physics. Physics can't be cheating. Get out of here.
So how do you do like a double bank?
Same thing. You'd have to go, okay, now it's going to follow this straight path to here, right? You'd have to have a team of 3. Yeah. Now, if you're trying to hit a double bank shot to avoid scratching, you're not a very good pool player. You haven't given yourself a very good lead in that case, yeah. Okay, so I'm actually going to show you guys just a quick video of what this looks like and how it looks.
Another thing is that like if you don't have friends, you can just get like the diamonds.
They got the little diamonds, yeah,
Yeah,
that's what the diamonds are for.
Yeah, like but there was the thing. Where is it? I think it was on YouTube somewhere. But like you can like subtract the amount of diamonds from like the other row that you're standing on, and that's where you know where to shoot.
You could just set your drink down.
It doesn't make any sense because I don't know how to do it. But like
I've never heard of that one before. I would avoid setting your drink down next to it because someone will knock it onto the pool table. Yeah, that's never happened, ever. All right, so I'm just going to show you a quick video here, guys, of kind of what. All right, so that has to do with reflection, which is one of the things that can happen when waves reach a boundary. There's always going to be some reflection, and there's always going to be some transmission. Okay, that is what happens to the waves that get past the boundary. Okay, if they get past the boundary, they're transmitted waves. Okay, a transmitted wave is always upright. That means it always is the same as the wave that came in. Okay, if that wave is upside down, then the wave that's in the new medium is upside down. Okay, or a trough. Okay, it's just upright just means it doesn't change. Frequency remains the same, we know that. Okay, the velocity is going to change, the wavelength is going to change, and amplitude is going to change as well. Okay, and the reason for that is the amplitude of a wave measures its energy. When a wave gets to a boundary and some of it reflects, that represents a loss of some of the wave's energy. So the amplitude is going to have to change as a result. Okay, and sometimes the amplitude changes because the wavelength changes. If the object slows down, it's going to squish the wave, okay, and the wave's going to get taller. Okay, if the wave speeds up, it's going to spread out, and the wave's going to be a little bit shorter. Okay, so amplitude is going to change as a result of both loss of energy as well as change in weight. Okay, we don't need to know about wave rays. We don't need to know about the normal. We've already talked about angle of incidence equaling angle of reflection. See how fast we can go, and we need to get through stuff. So, okay, now refraction. Refraction happens to transmitted waves. We really only see refraction if a wave comes in at an angle or obliquely. Okay, if it comes straight on, we don't observe it. Okay, all we see is that the speed of the waves change, the wavelength of the waves change, and that's it. Okay, but if a wave comes in obliquely or at an angle, part of the wave enters the new medium before the rest of it. So if these waves are going this direction, when this wave right here hits the new medium, this part of it slows down. This part of it keeps traveling at the speed of this medium. So this part of the wave falls behind. As they continue to travel, more of the wave enters the new medium and slows down. And so what you end up getting is the waves looking bent, okay, in the middle. And then eventually, once the whole wave has gotten into the new medium, what you get is that the wave actually changes direction entirely. Okay? This is the direction of the incoming waves. But the outgoing waves are traveling in a slightly different direction because they've been refracted or slowed down. That's what I was showing you with the laser pointer earlier. Okay? The speed of a wave, the wavelength of a wave are both changing here, but it's also changing their direction. It's kind of like what would happen if you were, it's kind of like what happens if you get your tire of your car, if you're driving on the road and on the shoulder it's snowy, but the lane is clear. If you get one tire in the snow, what can happen? Yeah, it'll pull you in, right? Okay? And the reason it pulls you in is because that side or that tire slows down. It can't go as fast as the rest of the car. The rest of the car tries to keep going fast. That part of the car slows and the whole thing rotates. Okay? And that's what's going on here. Part of the wave is getting caught and slowed down. The rest of the wave is still trying to go as fast as it was before, and it rotates the whole wave around and causes it to change direction. Okay? That make sense? So I'll show you, there's a couple of good shots in the video here of refraction. Okay, so we got these waves coming in. Okay, so these are our waves coming in. And then we've got, this is our boundary, and you'll be able to see already here that some of these waves have entered this new medium and they're not going the same direction. Okay, we've got, here's the incident wave, but this is the wave that's in the other medium. And it's already starting to bend a little bit, okay, because it's slowing down. Now, as I let it go, you'll see it really quite obvious here in a second. Okay, see how the wave bends in the middle, okay, right at the boundary? Okay. Okay, so light that's coming from this fish comes up to the border of the water, the boundary between the water and the air. And when it hits that boundary, it speeds up. Okay? And when it speeds up, it bends away from the normal. So this line that we kind of didn't talk about, the normal is what we measure everything from. It's perpendicular to the boundary. Okay? So the waves that are coming in have a very small angle, okay? And the waves that are coming out have a very big angle by comparison. Okay? They bend away from the normal, but my brain interprets that light travels in a straight line. So it tells me the fish is there instead of where it actually is. So when you're spearfishing, you can't aim for a fish. And the fish is deeper and closer. So you have to look at that fish and then try and stab closer to your own feet with the spear. It's very disconcerting. And that's just because of this refraction. And in fact, if you put the spear in the water, does it look like the spear bends? Right? I mean, you've all probably stuck a stick or something in the water. It looks like it bends when you put it in the water. Okay? It's just that the light that's coming from it is coming out of the water into the air, into your eyes, and it's getting bent as it does that. Okay, so if we have waves that are slowing down, okay, so in this case here, that's slow fast. Okay, from fast to slow. So if they're slowing down, my angle of incidence is going to be bigger than my angle of refraction. Not reflection, but refraction. Okay, that means that they are bending towards the normal. So in your notes here where it says from fast to slow, you might want to add bends towards the normal. Okay. So same thing is true here, right? This would be, okay, this would be my angle of incidence, and this would be my angle of refraction. It's much smaller than that because it's bent towards that normal line. If it goes the other way, okay, from slow to fast, okay, so now how can I tell that in this diagram the waves are going from slow to fast? What got bigger? The wavelength. Okay, that's how I can tell if they went from slow to fast. Okay, the waves coming in were short, the waves going out are longer. Okay, the other way I can tell is that my angle of incidence here is smaller than the angle of refraction. Okay, in this case, if you go from slow to fast, it bends away from the normal. Because it speeds up. And that's what makes you think the fish is closer to the surface than it actually is. Okay, so when waves approach a more dense medium at an angle, and the ray direction is not parallel, okay, the wavelength and the speed both change. And that's what we see actually in this picture here. So you can see that out here, the waves are actually pretty close together, but here at the shore, they look different, okay? And that's because near the shore, they're getting essentially slowed down. So out here, they're getting slowed down, and what that's doing is it's causing them to fan out. Out here, the waves can travel faster than they can here, and it's actually causing them to bend right around and come into this cove. Just like that video we watched the other day, the surfing video there. They were talking about how that one reef always made the waves get really, really tall. Okay? It's kind of a similar process. These waves come in, they get bent and focused and drawn around, and we can actually see that they get taller here than they are out here. Okay? That's because the water depth decreases. All right, this one's not in your notes, so I need you to copy this part down and do your best to draw this diagram. Okay, and then we'll talk about diffraction here in a minute. Our last behavior of waves here, guys, that we got to talk about is diffraction. Okay, now diffraction is something that only waves show. Okay, everything else we've talked about, refraction, reflection, waves and particles both do it. Okay, if I throw a ball at the wall, it reflects off at the same angle it came in at. Okay, it follows a particle. Right? If I throw a ball into the water, okay, and it's heavy enough, it'll refract. It won't follow the same path that it was having going in. Okay, so both waves and particles follow those behaviors. But diffraction is something only waves will show. Okay, and this is actually the behavior of waves that allowed Thomas Youngs to prove that light is a wave. Okay? Because for a very long time, the entire physics community, including Newton, believed light was a particle. Okay? Now, it's very logical to assume that light is a particle because we can't observe light diffracting. Okay? With sound and with water waves and things like that, we can observe diffraction. Okay? If I've got water waves, like you see in this picture on the right, coming towards this gap between these two rocks, okay, they go from being fairly straight to being quite curved. Okay? That's diffraction. Diffraction is the bending of a wave either around an object or through a narrow opening. Okay? This is why, unfortunately, in this room, we can hear everything that goes on in the girls' bathroom. Okay? Yes, we can. In case you didn't know that, we can hear everything that goes on in there if the door is open. Okay? And it's because of diffraction. The sound waves that occur inside that bathroom diffract out through the door. They go from being straight to being curved. And then they hit my door. And they do the same thing again. And they diffract even more. And so, unless I'm standing like right here in the room, I get to hear everything that is said in there. No, that's why my door is closed. Okay, I don't want to hear what's going on in there. It can be disturbing. Okay, so just be know, because sometimes people get talking in there, and they forget that they are making sounds that can travel and be heard, unfortunately, by me. And sometimes I hear things I don't want to hear. Okay. So just keep that in mind if you're ever gossiping in bed. Okay? Diffraction is a thing. Waves do it, sounds a wave, and I can hear you. Don't do it, please. Okay?
So this is probably a dumb question because I'm just trying to figure out like how this works. But if you had like 100 doors and one sound source, would it just keep going?
Yep. It would.
So you could literally just like amplify.
Wait, not amplifying. We're not amplifying. What I'm saying is that I can hear what happens in that bathroom because the waves come through my door and they become circular. They spread out, right? The only place I really wouldn't hear them would be right here because they wouldn't have had time to become circular by this spot here. But because they come through this door and diffract and become semicircular, they fill the whole room.
So
Okay?
if the school was made correctly, you could hear this bathroom all the way up in the math wing?
Theoretically, yes. Practically, no.
Okay.
Yeah. Okay? Now, does light do that? But it doesn't, it does, but it doesn't look like it, right? If I have a light outside this door and the door is open, there's a beam of light the exact shape of the door. Okay? It doesn't, the light doesn't like turn around and fill up the whole room from outside. Okay? So for a very long time, people said, no, light's not a wave because light doesn't diffract. If light diffracted, what would you not have following you around all the time? Right. Okay? Because look at here. Okay? If I'm this person and I bought the worst seats ever for this concert and I'm right behind this post, okay, I can still hear the concert. Okay? I can still hear the concert because the waves will bend around the post. Okay? And I'll still hear them. Right? But for a very long time, people said, hey, light doesn't do this. You have a shadow. Light travels through openings and makes beams. Okay? It doesn't diffract. And they weren't really wrong per se. They just couldn't observe the diffraction happening because of the nature of light. Light travels extremely fast and has an extremely short wavelength. Both of those properties reduce diffraction. The longer a wave is, the more it diffracts, because the longer it's in contact with the object or opening. So the opening or object can cause it to bend more because the wave is longer. Also, the slower the wave is, the more it will diffract because it's in contact with that object or opening for a longer period of time. A light wave travels through that door at 3.0 times 10 to the 8 meters per second. Its wavelength is like 10 to the minus 7 meters. Okay? So it gets through that door in no time at all. It has no time to diffract. Okay? Similarly, when I'm casting a shadow, okay, the light doesn't have time to diffract between my hand and the screen. Think how little time it takes the light to get past my hand to the screen. Okay? Traveling at the speed that light does. It just doesn't get a chance to diffract. But it actually does diffract. And it was Young's that proved it does. He observed water waves, sound waves. He knew that this is what waves do. And he said, I'm going to prove to you that light's a wave by making it diffract. So what he did is he set up what's now known as Young's double slit experiment. He made two walls, and each wall had narrow openings in it. So he had a light source here, and then he had a wall with a very narrow opening. And then in front of that, he had another wall that had two narrow openings. Okay? And he said, if light's a wave, I'll be able to put a screen here, and on that screen will be patterns of light and darkness like a zebra. And everybody, including Newton, looked at this experiment and went, did you fall down? Were you dropped on your head at any point? Because you're going to have this light source here and this hole. And the light's going to go through the hole and it's going to go right here. That's stupid. Okay? I mean, imagine the bullying this guy would have received, okay, from the physics community at that time. Okay? Because they would have logically assumed that's the dumbest thing ever. Like, we know what light does. It's not going to do anything. Your experiment's going to be over before it starts. Except he was right. Because what the light did, because these holes were so small and so close together, he was able to make the really short, really fast light waves diffract. Okay? And so what happened is the light went through here, and instead of just doing this and staying in a beam, it did what all waves do. It diffracted. Which means now these waves were able to hit these openings because they had become round. Right? And so what these two openings acted like were two separate speakers. Okay? And so we had waves coming from this speaker and waves coming from this speaker, or light waves in this case coming from each opening. And where those light waves overlap, there would be constructive interference and destructive interference. And so all that happened was, on his screen, he got areas of light and dark, light and dark, light and dark, based on where it was overlapping constructively and where it was overlapping destructively. Okay? But it proved unequivocally, light has to be a wave, otherwise how would it have gotten through the second set of slits? Okay? So diffraction is a really important, it's really important for basically that reason. It proved light is a wave, okay? But it's also a behavior that all waves show. Okay, so it's the bending of waves around an object or through a narrow opening. Okay, it's why we can hear sounds even if we're not in a direct line with the opening. Okay, it's why speakers are cone-shaped. It's why bullhorns are cone-shaped. Okay, like you've got a, the loudspeaker, that you put up to your face, you pull the trigger and it amplifies, same thing. Okay, we're trying to make the waves diffract and spread out. Okay, questions on diffraction? Okay, I want you guys to try a couple of these because these are the kinds of things I might ask on your test. Okay, draw a sketch of a trough approaching a fixed end. So basically what I mean is I've got like a slinky and it's tied to the wall and I make a trough. Okay, what's it going to look like before and after it hits the wall? Give you a minute on that one. Okay, so pretty straightforward question. Okay, I've got a trough. It's approaching a wall. That's my before picture. Okay, what's my after picture going to look like? After it hits the wall, it's going to go inverted and back the other way. So my second picture would be okay, I have an inverted pulse traveling backwards in the original medium. All right. Before, during, and after, complete destructive interference. Okay, so I want a before complete destructive interference, a during complete destructive interference, and an after complete destructive interference. So again, imagine this is like pulses on a slinky. Okay, so for this one here, okay, if they're going to interfere destructively, I've got to have pulses that are opposite. Okay, so I've got these two pulses which are opposite approaching each other. When they are interfering destructively, it would look like that. Okay, I could maybe add into there if I wanted to, like some dotted lines. Let's say that's where they would be, okay, if they were interfering destructively. And then the most important part, I have to demonstrate that afterwards, the two waves are unaffected. Okay? Yes, they pass through each other and interfere and cancel for an instant, okay? But afterwards they travel on, okay? Perfectly fine. Okay? Everybody okay with that one? All right, so for this one, so the before picture's on top, the after picture's on the bottom. Is this wave traveling into a a faster medium or a slower one? Slower. How do we know? There's a couple of reasons. It got shorter, smaller. Yeah, and it's right, so here's our original wave. Okay, it's quite long. Here the wave is quite short. We have quite a bit of wave energy being reflected back, and it's reflected back inverted. Okay, all of those are signs that this medium is slower than the first one. Okay, I'd ask you a very similar thing to that on your unit exam in a multiple choice question. Okay, so for this one, I send that pulse through the slinky. So I've got a slinky attached to a string, attached to a wall. Okay, when this pulse gets to the boundary between the slinky and the thread, okay, what's going to happen? Which would be easier for the wave to travel in, the thread or the slinky? The thread, yeah, it's much lighter. Okay, so is my reflection going to be upright or inverted? If I'm going from slow to fast? Upright. So I'm going to get a small upright reflected wave, and I'm going to get another wave that's upright that's traveling into the thread. Okay, when that pulse hits the wall, what's going to happen to it? It'll reflect inverted right when it comes up. Okay. All right. Okay, if I want to make the wavelength of waves on a rope longer, do I shake the rope faster or slower? Slower. Right, okay? I reduce the frequency, like I can change the frequency as the source, right? Then I'm making new waves, but they'll be longer because I'm not moving as fast. Okay, we'll leave it at that. I need you guys to clean off those desks so I can sanitize them before my science 10 come in.